So I think I'll wait just about 2 more minutes or so to the latest seminar on using Statgraphics. The topic today is implementing Lean Six Sigma using Statgraphics. I want to start this morning, or it may be afternoon where you are, by showing you a slide that I found in an IBM publication as I was searching around the internet, seeing what people had to say about Lean Six Sigma. And it's actually a pretty good diagram, I believe. It shows how Lean Six Sigma has been built from a lot of efforts and procedures and programs and methodologies that have gone before. IBM at least dates the evolution of Lean Six Sigma all the way back to the 1950s. It was in the 1950s that Deming and Duran first got people interested in using statistical techniques, analyzing data, in order to improve and maintain the quality of products that were being produced. Over the years between the 1950s and today, there have been quite a number of methodologies that have been devised. Just-in-time manufacturing, lean production, total quality management, and of course Six Sigma, developed by Motorola and GE in the 1980s and 1990s. Lean Six Sigma basically draws on all of these previous efforts in order to take the best of everything in order to maintain quality, maintain and improve product quality. Now, where Statgraphics comes in is primarily in 2 areas. In lean manufacturing, which focuses on reducing cost by optimizing one's processes. And secondly, Six Sigma, which primarily focuses on meeting customer requirements, meeting stakeholder expectations, improving quality by measuring, identifying, and eliminating sources of defects. And Lean Six Sigma brings together, as I said, the best techniques of lean manufacturing and Six Sigma and some of these other approaches to quality to produce an integrated approach to maintaining and improving quality. Now, if you're interested in reading this IBM publication, I'm giving you on the handout here, which you can download after the webinar is over, the link to that particular PDF file, which actually does a pretty good job, I think, of condensing the general ideas about what Lean Six Sigma is all about. For this seminar, we're obviously going to be concentrating on Statgraphics and what Statgraphics can do in order to give you all tools to implement Lean Six Sigma. Now, I'm going to be giving you 6 different examples of how you can use Statgraphics to apply Six Sigma techniques, Lean Six Sigma techniques. We're going to be showing you, first off, Statgraphics Centurion. Statgraphics Centurion is our standalone Windows application that has over 170 basic and advanced statistical procedures. The Statgraphics Centurion's been around for nearly 30 years now, and contains a full gamut of procedures that anyone master black belt or below needs in order to apply Lean Six Sigma techniques. It's a very broad-based statistical program. I'm also presenting for the first time today a new product that we've been working on. It's called Statgraphics Sigma Express. Now, what Statgraphics Sigma Express is, it's an add-in to Excel. So many of the folks that use Statgraphics also use Excel, and we've been asked on numerous occasions, could we put together access to Statgraphics as an add-in to Excel? So what we've done with Statgraphics Sigma Express is we've taken approximately 70 procedures out of Statgraphics Centurion, the most heavily used statistical procedures. Those that green belts and most black belts would need if they're learning or applying Lean Six Sigma techniques. Now, it's not in full release yet. We're still in the final testing stage. If you're interested, after you listen to the webinar and see some of the things I've done, you can send your contact information to info@statgraphics.com, and in a week or two we'll get you a pre-release evaluation copy that you can try out. Incidentally, it's available for Excel 2003, 2007, or 2010, and as you'll see, adds Statgraphics techniques to the Excel menus. Now, what I want to do, I don't want to waste a lot of time. I actually want to get into Statgraphics Centurion and Statgraphics Express and show you what we have in terms of Lean Six Sigma. So let me go first over to where I've loaded up Statgraphics Centurion, and you'll be able to see, if you look at the Statgraphics menu, that today, unlike the previous webinars I did, I'm going to be using what we call the Six Sigma menu. Now, the Six Sigma menu has standard menu items for File and Edit. It also, though, takes the statistical techniques and organizes them according to the DMAIC paradigm. There's a menu item for Define, for Measure, for Analyze, for Improve, for Control, the 5 steps in the Six Sigma DMAIC approach. There are also procedures for forecasting, things we call snap stats, tools where we'll find the Monte Carlo simulation, which is quite useful in Lean Six Sigma, and other standard menu items. Now, you can always switch between what we call the classic menu, the menu that lists basically file, edit, plot, describe, compare, relate, to the Six Sigma menu by going to Edit and selecting Preferences. There is a system option, a checkbox on the General tab of the Preferences dialog box to switch from the classic menu to the Six Sigma menu. And if you want to follow along or replicate what I have in this webinar later, you're going to want to switch from the classic menu over to the Six Sigma menu. Now, both menus give access to the same procedures. It's just they're organized under different menu headings, so that if you're trained in Six Sigma, you may be more comfortable using Define, Measure, Analyze, Improve, Control than using our classic menu headings. Okay. So there's Statgraphics Centurion. We're all used to looking at that. If I go down now and bring up Excel, now you'll see something new. And we did show this last week out in Pittsburgh at the ASQ World Conference on Quality. But this is the first that I'm actually showing this in a webinar. As I said, Statgraphics Six Sigma Express takes about 70 of the procedures most commonly used in Lean Six Sigma and adds them to the Microsoft Excel menu. You're looking here at Microsoft Excel 2007, and you can see a Statgraphics menu tab has been added to this Excel menu. The Statgraphics menu tab, the ribbon bar, has, again, menu items for Define, Measure, Analyze, Improve, Control. Also has Tools and Help. Now, the primary difference, other than the fact that the Express product is simply a subset of Statgraphics Centurion, is that in Microsoft Excel, we'll be entering the data directly into Excel and not transferring it to any application. In the Six Sigma Express product, you simply type your data into Excel and then pick something off the Statgraphics menu. In Statgraphics Centurion, you'd first move the data into our data sheet here, sometimes from Excel, but it can also be from an Oracle database or a text file or whatever. Move it into the Centurion data sheet and then call up the menu items. You'll see this. I'm going to be illustrating quite a number of different techniques here, so you'll see how it all works. Now, back to my PowerPoint slides for a moment. I'm going to be going through 6 different examples over the next hour, maybe a little longer than that, depending upon how much I have to say and how many questions you all have. And showing you some of the procedures that are quite commonly used in Lean Six Sigma. Now, the first procedure I'm going to show you is a cause and effect diagram. Now, a cause and effect diagram is meant to illustrate in an easy to understand way what different things cause some event. These are also sometimes called fishbone diagrams or Ishikawa diagrams, and they illustrate the causes of specific events. For example, I may be wondering what causes defects in my product. There may be a number of major causes of defects. It might be material, personnel, environment, machines, etc. And in order to brainstorm the process and begin to understand all the causes of the events, I'd like to create a diagram something like this. Now, let me show you how that typically would be done first in Statgraphics Centurion. In Statgraphics Centurion, I'd start first with an empty data sheet. I'd then create a column, and the column I'm going to call Labels. I double-clicked on that column header. I'm going to define a column called Labels, and I'm going to set it to character so that I can type in character data. The first row will contain the label for the event. So if I want to predict what causes product defects, I'll type in defects. Now, after I have the event typed in the first row, I'll go to the Define menu, and here you'll see an option for cause and effect diagram. Now it says cause and effect diagram on the menu. I see it says fishbone diagram on the dialog box. Obviously both terms will work. The way this begins is you take the column called Labels, put it into the Labels field, and press OK. Now what this will do is this will open up what Statgraphics Centurion calls an analysis window. And you'll see the beginning of a fishbone diagram to the right, an arrow with the event labeled defect on the far right. Now I'm going to move this slider bar a little bit to the left to give myself a little more room to work. I'll then press the right mouse button and go to Analysis Options. Now Analysis Options opens up a dialog box that will allow me to create a fishbone diagram. And it works like this. There are 3 fields on the dialog box for causes that affect the event. Primary causes, secondary causes, and tertiary causes. To create the fishbone diagram, we normally start by defining the primary causes. So I'll push the Add button, and I'll put in as my first primary cause, materials. My second primary cause, let's make that personnel. Third primary cause, environment. I'll try to spell this correctly. And then finally, the fourth cause, machines. And you can add as many as you like. After you get the primary causes typed in, you can go push the redraw button, and you'll see it'll now draw some ribs on that fishbone diagram for each of the primary causes. Now we'll take each primary cause and define the secondary causes. Well, I don't want to do all of this. It'll take too long. I'll start, though, and click first on personnel. Then I'll go to the secondary causes field, push the Add button. And let's see. This is for personnel. So one cause for personnel could be shifts. How about training? And how about operators as a third secondary cause? Push redraw, and you can see it's going to be building up the fishbone diagram. And then finally, I can take a particular secondary cause and then go over to the tertiary causes section and add in some third-level causes. For example, part-time and perhaps full-time. Again, redraw, and you can see it's added now a third level of spokes to the fishbone diagram. Now this we would call the cause and effect wizard, and it's meant to make it simple for you to define the causes of a particular defect. Okay, now if you'd like to see how the data's been structured, if I go back to the data book, what it's actually done is create a column with various labels. You can see in addition to the word defect, it's now added in the primary causes, the secondary causes, and the tertiary causes. When it redraws, it simply reads that information, and you can see that we're using periods and double periods in our data structure to define what's a secondary or a primary cause. Now, if I wanted to do the same thing from the Statgraphics Express product, I could go to Microsoft Excel. Go to the Statgraphics menu. Now, we had a little bit of a debate where we should put the cause and effect diagram, and as I remember, it actually got put under the Improved menu. So if you go to the Statgraphics Excel menu now, you can go to cause and effect, and there are actually two options. There's a templates option, which will pull up an Excel template where you can just fill in the information. And there's the wizard. The wizard option would give me access to exactly what we went through with Centurion. On the other hand, if you were to push template, what that would do is that would load up into an Excel worksheet a predefined template for the cause and effect diagram, which you could then just go in and begin to modify. Now, if you're happy with the Excel drawing tools, and I know there are a lot of people who've done amazing things with the Excel drawing tools, this is a template which you can now go in and modify any way you want. You can go in and start adding labels. You can resize things. You can move ribs around. You can eliminate. You can add, and so forth. So in addition to the sequence of dialog boxes that I showed you with Statgraphics Centurion, Express also offers in some procedures, like cause and effect diagram, FMEA, process mapping, affinity diagram, and so forth, templates which are predefined Excel worksheets that you can simply go in and edit. Again, what we tried to do with the Express product is make it very simple for people that are already familiar with Excel to start to do some Lean Six Sigma. Okay, now, again, I will remind you, after this webinar is over, you can download my PowerPoint presentation here. And what I've done is try to give you some views of some of the major screens that I've gone through. Okay, another important example, a second example of statistical procedures for use in Lean Six Sigma comes from the Measure menu. And it's under Gauge Studies. Now, Gauge Studies refers to the process of evaluating measurement error. And, in order to apply statistical process control, in order to apply design of experiments and so forth, we need to be capable of measuring what we're interested in well enough that if we see a change, it's likely to be a real change and not just measurement error. I know a lot of people jump into SPC and DOE without really knowing whether their measurement processes are precise enough to get anything useful out of those SPC and DOE techniques. So gauge studies are important if you have any sort of measurement error, which most of us do. Now, in Statgraphics, we have quite a number of different procedures for doing gauge studies. They all follow the AIAG guidelines. That's the Automotive Industry Action Group, made up initially of the big three automotive companies out in Detroit in order for their suppliers to have a standard way of doing gauge studies. We have in Statgraphics a procedure that will help you set up a gauge study. It creates a basic data template. And then we have procedures for analyzing both variable data, that's measurement type data, and for analyzing attribute data. Attribute data is basically data where you look at an item and you say, oh, that's a good one, or no, that's a bad one. Pass-fail type data. Now, in Statgraphics Centurion, we have a full set of procedures. In the Sigma Express product, it's a scaled-down version. As far as the analysis of variable data, which is the most common, where we're taking measurements, Statgraphics offers an average and range method and an ANOVA method to evaluate R&R, repeatability and reproducibility, based upon a full study. Now, in a full gauge study, we go out and find a number of different operators. Each of those operators evaluates a set of parts multiple times. And based upon the differences or similarity of their measurements, we get an idea of how good the measurement process is at separating good items from bad items. Now, if it's that applies both to variable data, where operators go out and actually make measurements, and also to attribute data, where appraisers go out and look at an item, the same item, several times, and hopefully come up with consistent appraisals. Statgraphics also has a range method that is based upon just two operators measuring a set of parts one time each. Now, all of those procedures actually get into variability or precision. There's an additional procedure also in Statgraphics, I'm not going to be able to talk about it today, called gauge linearity and accuracy, that gets at the bias of a measurement process. Now, to get at the bias of a process, one normally needs a set of golden samples where you know what the results are supposed to be, and then you can compare your measurements to the known values for those items. Now, when we think about gauge studies from a statistical point of view, I normally think about it using these two formulas. I think about the total variability in my measurements. Suppose I go out, I do a big gauge study, and I come back with a bunch of measurements. The variability amongst those measurements consists of two components. It consists of real variability from one item to another item to another item to another item. And it also consists of error coming from the measurement process. One of the goals of a gauge study is to be sure that the measurement process component, variance component, doesn't swamp the real variability amongst the product. If most of what I see in my data is just measurement error, then I really won't be able to know what parts are good, what parts are bad, or see the effect of making changes. Secondarily, if I look at the measurement error, that variability is normally thought to consist of two components. Repeatability, which is the variability I see when the same person looks at the same item more than once. And sometimes, if they look at the same item more than once, they come up with different results. On the other hand, reproducibility is operator-to-operator variability. How much does the result or the measurement of one operator differ from another? Now, let me show you how Statgraphics works with respect to setting up and analyzing a typical gauge study. Okay? And I'm going to do this probably using the Express product. It works pretty much the same in both Centurion and Express. Just to give you a little bit of an idea, if you've not seen the Express product, and I don't think most of you have, how we would set up a gauge study. Now, the first thing we would do is we'd find an empty data sheet in Excel. We'd then go to Measure down to the section on Gauge R&R. You can see under Gauge R&R there's a procedure for data setup, for average and range method, for ANOVA method, for range method. And as I said, I'm going to start with data setup, so I'll ask for the data setup. Now at this point, it's going to bring up a dialog box for me to define the gauge study. Those of you who've done this in Statgraphics Centurion will notice that it's actually the exact same dialog box that Centurion would offer at this point. What I need to tell it in a full gauge study is how many operators I have, how many parts each one will measure, and how many trials there'll be. How many times will each operator measure each part? A very standard gauge study is 3 operators, 10 parts, 3 trials. I have a choice over here on the upper right of whether to set the data up as a data column and a code column. That would mean I'd have one column for all my measurements, another column identifying the operator, another column identifying the part, and so forth. Or whether I'd rather put all the measurements for a single part in one row. I think I'll do it the latter way. I can also randomize the trials. I could include a column for reference values. That would be known values if I actually knew what the value should be for each of the parts. Let's just go ahead, though, and press OK. The next dialog box asks me to name the operators, and I think I'll name them Ann, Bob, and Carlos. That's a good A, B, and C, and then press OK. Now you'll see a message coming from Statgraphics that the gauge study has been copied to the Windows clipboard. Please paste it into an empty data sheet in your workbook. If I press OK, I'll get a summary window, but more importantly, I can go back to my Excel spreadsheet, go to the upper right, push my right mouse button, and press Paste. And what it will do is it will paste into the data sheet the format that Statgraphics wants for its gauge studies. Now you can see this is a standard Statgraphics format where row 1 has a name for each of the columns. Row 2 has units, if there are any units. Now, none of these columns have units, although I could enter them if I wanted to. But then a section here for the 10 parts. And you can see what I asked is that for each of the 3 operators, Ann, Bob, and Carlos, to measure each of the 10 parts 3 times. So it's basically set up a data structure, and now I would go ahead, measure those parts, and put in the results. Now, we don't want to waste a lot of time doing that, so I'll tell you what. I've actually already created an Excel file with some data in it. So let me go to Excel here, and there it is. I have an Excel file already created called gagestudy.xls. Let's open that up. And there it is. That's the same basic data structure. We're now we have a section of measurements. Now, in the Excel product, the Statgraphics Sigma Express product, in order to analyze data, the first thing you would typically do is you'd highlight it. I'll highlight the rows and columns that I want to analyze. I'll then go to Measure, Gauge R&R, and now I can pick one of the analytical methods. I think I'll start with the ANOVA method here. Now, the first thing Statgraphics Express needs to know, since the data is in Excel, is what type of structure does your Excel spreadsheet have? Does it have column names? Does it have names and comments? Or did you highlight just data? Well, in this case, I have a row for names and a row for comments. So I'll take that choice. It also needs to know how the data is set up. Is it data in code columns, or is it one row per part? Well, you'll remember I created it as one row per part, so I'll analyze that. It'll now come up with a final dialog box where it wants to know what columns have the data, what columns have part identifiers, and so forth. If I highlight the first 1, 2, 3 operators, 9 columns, and put it in the data field, put the parts number in the parts field, and press OK, I've now defined the data. One final dialog box when you're doing an analysis of a gauge study like this: what structure is the data? Do we have a cross structure? Do we have a nested structure? Now, in a cross structure, each operator will measure the same parts. In a nested structure, each operator measures different parts. This is crossed. Each of the operators measure the same 10 parts. I can also tell it whether or not I want to estimate an interaction. That's an interaction between parts and operators. Typically, I would not, so I'm going to leave that just the way it was. And finally, I can type in a tolerance. Now, the tolerance is the distance from your lower specification limit to your upper specification limit. For this particular data, I'm assuming that the spec was plus or minus 20, so that's a distance a tolerance of 40. Go ahead, press OK, and one more dialog box. Just as it would be in Statgraphics Centurion, it wants to know what tables I'd like, what graphs I'd like, and I think I'll ask for an analysis summary, a tolerance analysis, and an R&R plot. And once I've selected those, it's going to pop up an analysis window with multiple panes. Now, at this point, it's going to look just like Statgraphics Centurion. I'm going to get the exact same output, the exact same options. The only difference was the data was coming directly from Excel and the menu was on Excel. And you can see some of the important results for a gauge study. Here's an R&R plot. On a gauge R&R plot, we first take the measurements and we subtract away the average. So what you see on the vertical axis here is the deviation of each measurement from the average of all the measurements. We then plot by operator the 3 measurements on each of the 10 parts. Now, what you can see is there is some significant difference between the operators. Ann tends to measure a little lower on average than Bob, and Carlos is about in the middle. You can see also by the height of the box that Bob's a little bit more variable, perhaps, than Ann and Carlos in the measurements. If you want to look at some of the important numerical results, these are the same numerical results as you'd see in Statgraphics Centurion. What's particularly critical are the numbers in red, obviously. Here you see, for example, sigma R&R. It looks like the standard deviation of the measurement process is about 1.16. The standard deviation overall about 3.37. The ratio of R&R to total is about 35%. Now, this is one of those interesting statistics that the AIAG recommends that you calculate. And they normally say that in a good measurement process, the measurement variability ought not to be any more than 10% of the overall variability. They go on to say at other times up to 30% may be acceptable, but I'm way past that. I'm at about 35%. There's also a statistic down here called number of distinct categories that tells me basically how many groups I can separate my items into. It says that this measurement process is capable of taking the items I've measured and separating them into 3 groups, like big, small, and medium. Well, again, the AIAG says that should be at least 5. So this particular process, measurement process, is actually not all that good. There's also a tolerance analysis here with an important statistic right down here. Again, it's in red under the tolerance analysis. It's called the percent of tolerance, or sometimes the tolerance ratio, or precision to tolerance ratio more precisely. It's a number here as a percentage, and it says right now 17.4. This says that the measurement process covers about 17.5% of my tolerance. If I look at the tolerance, which I input as 40, it actually takes 6 standard deviations, compares it to the tolerance. And again, the AIAG would like to see that number down below 10%. 17.5 is a little high, but it's better than the 34% we saw before. So that's a standard gauge R&R, which is a very important sort of thing to do when you're doing Lean Six Sigma before you do anything else. Now, back to PowerPoint for a moment. That's the gauge study. A third example that I think would be quite interesting for you all to look at would be a capability analysis. Now, I did a seminar, a webinar a couple of weeks ago, I believe, on doing a capability analysis. A capability analysis basically takes a set of measurements and compares it to a set of specification limits. And in Six Sigma, the primary statistic that one gets out of a capability analysis is something called DPMO. DPMO stands for defects per million opportunities. And it basically says if I take my items, all the items I've produced, and look at the different opportunities for those items to be defective. And by defective, what we mean is not conforming to a specification. Some people don't like the word defect, because just because you're out of spec doesn't necessarily imply that you're defective. But in Six Sigma terms, a defect is the standard terminology. So anyway, I'll look at a certain number of items. I'll look at every opportunity for those items to be out of spec and count how often out of every million opportunities I don't conform to the spec. As defined by Six Sigma, world-class quality is 3.4 defects per million or less. If we're producing at what's called the Six Sigma level, then we have a DPMO of no more than 3.4. Now, that's a very tough target, and there are cases where you can still have good product and be well above 3.4, but it serves as a good target for what's called world-class quality. Now, the data I want to look at is data that you might have seen before. I've taken a sample of 100 electronic components, and I've measured the resistivity of each of the 100 components. I'm going to assume that there's an upper specification limit on resistivity. Anything above 500 is bad. Anything below 500 is okay. I'd like to know, based upon my sample of 100 electronic components, how many components per million are likely to be above that specification limit. Okay, now let's do this first off in Statgraphics Centurion. Now I realized as I was going through preparation of this that I need a different icon for the Express product than for Centurion because I have a hard time sometimes finding the right window. Okay, here we go though. Let's empty out Statgraphics Centurion, go back to an empty spreadsheet, and let's open up a data file called resistivity. There we go. Here you see 100 measurements of the resistivity of electronic components. Now there are a number of places in Statgraphics where one can do a capability analysis. And again, I did a webinar not too long ago on capability analysis. One thing I didn't show you though, I didn't show you the snapstat. At least I don't remember showing it to you. So what I'm going to do now is I'm going to go to the snapstats menu, and in this case call up capability assessment for individuals. Now snapstats are actually scaled down versions of other Centurion procedures. Scaled down in the sense that they have less options, but they have the advantage of producing one pre-formatted page of output. Now what I'm going to be looking at, I'm going to be looking at resistivity, that's my data, as a function of date. I can enter a lower specification limit, a target value, or an upper specification limit. In this case, I have an upper specification limit. Okay. Now, I can base my capability analysis on any of 27 different probability distributions. If I knew it was something other than a normal distribution, I might pick something else. Or I could choose perhaps a power transformation, a log transformation, or a square root, or box-cox, or whatever. If I don't know what to choose in Statgraphics, it's usually a good idea just to take the defaults. And when I press OK, what's going to pop up here for me now is one pre-formatted page of output. Now, what you can see here at the top left is it says that there was a sample of 100 observations. The mean was 235.25. Okay. The specification was 500. 1% of the product was observed to be out of spec for a z-score of 3.68. 3.68 means the upper spec is 3.68 standard deviations away from the mean. It also estimates for me what's called long-term capability and short-term capability. Long-term capability basically looks at the entire data collection period. Now, the data collection period here was from January through March. And what it does is it takes the standard deviation over that entire period. Based upon that, estimates 116 defects per million. It also comes up with a short-term capability estimate. And the short-term capability, what it does is it looks at the variability, not over the entire sampling period, but the variability between observations close together in time. Now, technically, in this case, it's estimating sigma from the moving range. What's important to us, though, is it estimates a defects per million of about 106 in the short term. Now, if a process is in a state of statistical control, both short-term and long-term capability will be similar. Unfortunately, if the process were out of control, long-term performance might be a lot worse than short-term capability. In either case, I'm somewhat above 3.4 defects per million, somewhere in the neighborhood of 110 defects per million. Now, that's based on the assumption of a normal distribution. If you look down a little farther here, though, you'll see a histogram of the data with the best fitting normal distribution. And actually, that's not all that great a fit. You can probably see it even better by looking at the probability plot down here. A probability plot, a normal probability plot, is scaled such that the points come from a normal distribution, they ought to fall approximately along a straight line. Now, unfortunately, in this case, there's quite a bit of curvature, leading me to believe that the normal distribution is really not the best model for the data. Okay. Now, I mentioned that there are a couple approaches, I think, for dealing with non-normal data in the last webinar. One approach is to press the right mouse button, call up analysis options, and ask for a different distribution. And you might remember that last time I believe we found out that the largest extreme value distribution was a good distribution for this particular data. Another possible approach, though, is to transform the data, to take a log or some power of the data such that after we raise the data to a power, after we transform the data, the transformed values are approximately normal. Box and Cox have a procedure where they will actually automatically find for you the best power. And that's what I'm going to do here. I'm going to push Box Cox and press OK. And you will see now it'll switch from a normal distribution to a non-normal distribution. It says the Box Cox optimized power is minus 0.4. Which means if I take resistivity and raise it to the minus 0.4 power, I will have approximate normality. Now, in the original metric, that implies a skewed distribution, as you see here. But look at that normal probability plot. Look at how nice everything is once one transforms resistivity. The transformed values of resistivity are actually quite normal. Now, unfortunately, if one looks at the defects per million, you're not going to like it nearly as much. It says now about 7,000, almost 9,000 defects per million. And the problem here is that before I assumed a normal distribution, so I had an equally long upper and lower tail. After transforming the data, the implicit distribution for the data is skewed to the right, and there's a lot more probability above the upper tail. So although I don't like it, I don't like the 9,000 defects per million compared to the 100 I got when I assumed the normal distribution, you can tell by the probability plot that this is a much more appropriate analysis. Now, to do the similar sort of thing in our Express product, I could go back to Excel. I could go back to Excel and open up a data file called resistivity.xls. This is the same data in an Excel file. Now, we've added to the Express product a few new statistical procedures called statlets. And if I go to the Analyze menu to Process Capability down to Capability Statlet, you'll see a new procedure that will eventually make its way into Centurion, but we're testing now in the Express product. What statlets are, well, you'll see them in just a minute. When I pick the menu, though, the first thing it's going to ask me, again, is what's the data structure look like? Well, in this particular data file, I have simply column names. It's going to want to know where is the data, what's the time scale, and what are the specs, just like the procedure I showed you a moment ago. But when I press OK now, it's going to open up an interactive graphical window. Now, a statlet is defined as a statistical procedure, an interactive statistical procedure that runs in a window with an interactive toolbar. You can see the same data. You can see the normal distribution. This, incidentally, these short vertical lines are at plus and minus 3 standard deviations. You can see the spec. To the right-hand side of the graph, we're showing you, again, long-term defects per million, short-term defects per million. We're also showing you, though, goodness of fit statistics for that normal distribution. We're showing you p-values for the Shapiro-Wilk test, which is a test of normality, a very powerful test for normality, and the p-value for a more general goodness of fit test, a Kolmogorov-Smirnov test. Now, what's interesting about the statlets, take a look at that Shapiro-Wilks value. The way that the p-value for Shapiro-Wilks works, if it's less than 0.05, the normal distribution does not fit, is not significantly good or significantly bad at the 5% level. Now, up here I have a slider bar that I can use to change the power to which the data is raised. And as I start changing the power, you can see the distribution becoming more and more skewed to the right. You can also see the Shapiro-Wilks value getting larger and larger. Well, this is essentially what Box and Cox do. And you'll see at some point that Shapiro-Wilks value will stop getting bigger and start getting smaller. There it is. And wouldn't you know it, it's the data raised to the minus 0.4 power. And now you see those same numbers on DPM. So what we are trying to do, and you'll see this in the next version of Centurion as well, these statlets will find their way in there, is do a lot more interactive manipulation of the graphs so that you can get a good idea, for example, of what a Box-Cox transformation is trying to show you. Okay. All right. Well, that's an example of a capability study, which is another procedure that's very commonly used in Lean Six Sigma. A fourth procedure commonly used in Six Sigma is design of experiments. In the improve section of the DMAIC paradigm, one of the things that's often done is the creation and analysis of a designed experiment. Now, I've already done a webinar where I've showed you how Statgraphics Centurion can set up different types of experimental designs. And 3 weeks from now, we're going to do another DOE webinar on RPD designs, robust parameter designs. So I thought here I would quickly show you what we've done with the Statgraphics Express product. Now, if I can go back to Excel, if I'm going to set up a experimental design in Excel, I'll normally find myself first in empty data sheet. I'll then go to the Improve menu, and you'll see under Improve options to create and analyze an experiment. If I ask to create an experiment, it's going to step me through several dialog boxes. The first dialog box will be used to define the response variables. And I'm going to set up very quickly an experimental design here to measure the yield of my process in grams and the strength, for example, in pounds per square inch. The second dialog box will allow me to define the experimental factors to be changed during the experiment. Now, if you're familiar with the Statgraphics DOE Wizard, which I showed a couple of weeks ago, you'll notice that this is actually a scaled-down version of the Wizard. Here, we can handle up to 8 experimental factors. Each experimental factor has a name, and I'm going to put in 5 names. How about temperature, flow rate, concentration, agitation rate, and catalyst. I'll also put in, well, I can define any of the factors as either being categorical or continuous, as in the DOE Wizard and Centurion. In my case, all three factors will be continuous, so I'll define a range over which those factors will be changed. So I'm putting in different ranges here for each of the 5 experimental factors, 1.0 and 1.5. Okay? So now I've defined the response variables. I've defined the experimental factors. One more dialog box. Select the design. Now in the Express product, we're going to limit the designs to either screening designs or optimization designs. And depending upon which type you choose, there'll be a suggested design, or you can ask for more choices. Again, we've decided, and I think it's right, that for a lot of people just learning Six Sigma, we shouldn't give them a list of 16 different designs and expect them to choose the best. So we're going to give them a suggested design. I can also throw in a few additional center points if I want. But basically, I can just take the defaults if I like, press OK, and it will create the design. It'll create the design, also put it on the Windows clipboard, so if I go back to Excel, I can just say right mouse paste, and my experimental design is now in my Excel worksheet. Not all the bells and whistles you'll find in Statgraphics Centurion, but certainly about as easy as it could be to create a good experimental design. Now, when it comes time to analyze it, you're going to see the same sorts of features that you see in Statgraphics Centurion. And rather than taking time to type in the data, let me just load again an Excel file where I have some results. When it's time to analyze the data, we'll go to Improve, Analyze Experiment. Tell it a little bit about what the header is, and in this case, it's column names and comments. Pick the response variable we're interested in, the experimental factors we're interested in. Press OK. Select a set of tables and a set of graphs. Press OK. And up will pop the same sort of standard analysis you'd see from the Statgraphics Centurion product. You see, for example, here a ANOVA table, and it shows an R squared actually of about 99.5%. Pretty good fit, huh? One new thing we've done here is we've actually highlighted in red all factors that have a significant p-value. But you've got the same sort of output in general that you'd see in the Express product. And one of the things we consciously did when designing the Express product is not to use Excel graphics, to use our own graphics. That enables us to do the same sort of interaction with the graphs that we tend to do in the standalone Windows product. I mean, I can go in here, I can change things around, I can color code the heights of the surface, I can go into the Response Surface Explorer and change levels of the factors to see what the effect would be on the surface. All the sorts of things I demonstrated in the Design of Experiments seminar are available here because we're running in our own window. Then when I'm ready to take this graph, I can go to the graph, I can right mouse copy, go back to Excel, do a right mouse paste, and there's the graph in Excel. So rather than trying to rely on Excel graphics that just don't have the capability of doing the sorts of interactions that we want to do, we do the graphics in our own window and then simply copy the results back to Excel. Okay. Well, that's a quick setup and analysis of an experiment, showing you how that's done. Two more examples I want to show you very quickly. So far we've done examples from Define, Measure, Analyze, and Improve. One final example from the domain menu has to do with control charts. And this example is in honor of Stu Hunter. Stu Hunter was my major professor at Princeton when I first took statistics. Got me interested in the whole subject. Happened to see him out in Pittsburgh last week. He's still in great shape and still going strong, getting around, giving talks, and so forth. One of the things that Stu was particularly interested in over the years was time series analysis and how they applied to control charts. And one of his suggestions was that whenever one did a control chart, as you would do in Lean Six Sigma when you got to the control section, is that in addition to plotting the data, you plot something called an EWMA. Now an EWMA, that stands for exponentially weighted moving average. And the interesting thing about adding an EWMA to a standard control chart is that it helps you see trend in addition to your occasional outliers or unusual events. Now, I want to go over to Statgraphics Centurion, if I can. Again, I need a different icon for the Express product. There we are. Here's Statgraphics Centurion. And clear out the example that we were working on, the capability example, and now load up a data file called bottles. Now what bottles is, it's a measurement of the breaking strength of a sample of glass bottles taken once every 10 minutes. So you see the measured breaking strength in pounds per square inch. There are a total of 100 samples 10 minutes apart. Under the control menu, we'll see all of the Statgraphics control charts, and there's all sorts. There are standard X bar and R charts, individuals charts, P charts, EWMA charts, Q sums, toolware charts, more control charts, and well, I know it's more control charts than you'll find anywhere else. To do a standard control chart for this sort of data, though, I'd pick individuals. I tell it where my data was, how to label the x-axis, press OK. Now in Statgraphics, when we do a control chart, we distinguish between what we call initial studies and control to standard. In an initial study, we'll let the data decide where the control limit should be. Some people call them phase 1 studies. In a control to standard, which some people call phase 2 studies, we'll tell it where the control limits should be by basically telling it what the mean and standard deviation is of my process when it's in a state of control. I may have to do a whole webinar on control charts at some point. Anyway, suffice it to say that we're going to let the data determine where the control limits are, so we're going to do an initial study. Now we can define different types of tables and graphs. I'll just take all the defaults, and what it'll do for an individual's data is it'll come up with an X chart and an MR2 chart. Now here is the X chart. It plots the individual 100 measurements. The center line is at the mean of all the data. That's X bar. And the standard, the control limits are at plus and minus 3 standard deviations. Now, one of the problems with plus and minus 3 standard deviations is they're pretty wide when you're plotting just one observation each at a period of time. So what Stu Hunter suggested is we add something to this chart. We push the right mouse button, go to Pane Options, and add an exponentially weighted moving average. Now, an EWMA is a weighted moving average where we take the most recent observation and average it with all of the past observations. But not an ordinary average, a weighted average, whereas you go back into the past, the weights fall off. That gives the most recent data more weight than the past data. Well, how fast those weights fall off is determined by something called lambda. And what Stu suggested is that we set lambda at 0.2. Now, why 0.2? Okay, well, I'll show you why in a second. Let's put it on here first. And actually, let me right-click, go to Graphics Options, go to Lines. Line 18 is the moving average. I'm going to thicken that out a little bit so you can see it more easily. There you go. What we've now added to the control chart is the exponentially weighted moving average. That is the average of the most recent observations and all the past observations. At any point in time, it averages most recent and all past, with weights falling back into the past. Well, the neat thing that Stu suggested is if you use the value 0.2 for lambda, then the inner warning limits, what would ordinarily be the inner warning limits on your control chart, which are lines at plus and minus 1 sigma, are actually the 3 sigma limits for the EWMA. So at the same time that I'm looking at individual observations to see whether anybody's beyond 3 sigma, I can look at a smooth history of the process and see whether it's beyond 3 sigma. And actually, I usually like to go back here and actually color the zones, which makes it even more apparent. So you've got a dual-purpose control chart here. You've got an individual's chart, and any point in the red zone would be beyond the 3 sigma limits. And you've got an EWMA in the middle, and any time the EWMA went outside the 1 sigma zone, okay, in its metric, it would be also beyond its 3 standard error limit. Now, this is quite a well-behaved series. The only thing you can object to here, you see a few red stars. Those are some runs rules violations, where you have, for example, a certain number of points beyond 2 standard deviations or 1 standard deviation. There's some runs rules violations, but otherwise it's sort of a neat application of control charts. Okay. Well, I apologize for running a little long. I always run a little long because I get excited about these things. There is one more example, though, that I have to show you. Everything I showed you so far is pretty much straight 6 sigma. DMAIC, define, measure, analyze, improve, control. If we start talking about process optimization, lean manufacturing, and so forth, one of the interesting things that one begins to need to do is what's called Monte Carlo simulation. A Monte Carlo simulation is used when you're trying to discover the distribution of something that's perhaps too difficult to analyze analytically. Now, I've taken a relatively simple example to show you how it works, but a popular example anyway, and it has to do with analyzing cycle times. Let's suppose that when we produce something, that there are 4 different steps required to create this item. Step 1, Step 2, Step 3, Step 4. Step 1 needs to be done first. After it's complete, we can then do Step 2. After Step 2 is complete, we can do both Step 3 and Step 4 at the same time. Let's assume that the length of time it takes to complete Step 1 follows a normal distribution with the means and standard deviations that I'm showing you. The time to accomplish Step 2 is also normal. The time to accomplish Step 3, let's assume an exponential distribution, and Step 4, a uniform distribution. The total time to get through the cycle is then the length of time it takes to do Step 1, plus the length of time to do Step 2, plus the greater of the length of time it takes to do Step 3 and Step 4. And this is what makes the analysis a little bit more complicated. And let's suppose I'm interested in knowing what the mean and standard deviation will be of cycle time. Now, both our Centurion and Express products allow you to do this sort of Monte Carlo simulation. I decided that I would try it using Centurion. It works exactly the same. But since most of you are right now using Statgraphics Centurion, let's show you how it's done in Centurion. Well, the first thing is you get yourself an empty data sheet. The second thing is you start and define each of the variables in your simulation. Now, I'm defining a column actually called step 1, another called step 2, another called step 3, another called step 4. The fifth column I'm going to call the longer of 3, 4. It's going to be a column in which I put the greater value of step 3 or step 4. And then 6, we're going to call cycle time. Okay. So I've set up actually 6 columns in an empty data sheet. I'll now go to the Tools menu to the section on Monte Carlo simulation. And what I want to do is I want to do a general simulation model. Okay, if I pick general simulation model, a new window will open. And if you read the instructions, it'll tell you push the button to define your input dialog. Now on this input dialog, I define, based upon the names I've already created, the variables in my simulation. And I have 6 variables in this particular simulation. Step 1, I'm going to assume follows a normal distribution with a mean of, let me look at my notes here and see what the mean was. It was 12.1 and the standard deviation was 1.9. Okay? For each input variable, I'm going to tell it what distribution I assume it follows. Now, it could be a constant, but most of the time, it's going to be a distribution. And this one also was normal 7.3, 0.5. Step 3, I'm going to assume was exponential. Exponential has a scale parameter, the inverse of which is the mean. So if I put in 0.2, that's a mean of 5. Threshold is a minimum value. I'm going to set that to 0. Step 4, this is going to be uniform. Again, I'm following what I had on the previous slide. Lower limit of 2, upper limit of 6. So I'm equally likely to get any value between 2 and 6. Okay. All 4 of those first 4 variables follow probability distributions. Now, in terms of the longer of 3 and 4, that's going to be a function. And now the way I'm going to define this function is I'm going to use Statgraphics lingo to define it. I'm going to say that this function is step 3 times step 3 greater or equal to step 4. Step 3 greater or equal to step 4 is true or false. 1 if true, 0 if false. So only if that's true am I going to get step 3, otherwise I'll get nothing. I'll get 0. Then I'll say plus step 4 times step 4 greater than step 3. Okay? And let's see if it likes that function. Oh, I put that in the wrong spot. Oh, no, I put it in the right spot. Longer of 3 and 4. It's step 3 times step 3 greater or equal to step 4 plus step 4 times step 4 greater than step 3. So it's going to pick up the larger of columns 3 and 4. The last column I'll need to define is cycle time. That'll be also a function. That'll be step 1 plus step 2 plus the longer of 3 and 4. Press OK, press OK. I've now defined my simulation. I'll now press the right mouse button, go to Analysis Options, and ask it to generate 10,000 samples, which it just did, and put in my cycle time column. You can see all 10,000 observations. It's step 1 plus step 2 plus the longer of step 3 and step 4. And if I go back to the window, I can also ask for some more output. I can ask for summary statistics and a frequency histogram. And you can see the average cycle time is 25.74, a standard deviation of 4.72. And finally, the distribution, you can see values pretty much as short as 16 all the way up to about 70. And that's because of that exponential distribution. Well, that's the final example I wanted to show you. Again, I apologize for running a little bit long, but I did want you to see a number of different examples from Statgraphics and Shurian and also Statgraphics Express, give you an idea of what Statgraphics can do for you in order to apply Lean Six Sigma. Now, more information, you can find a lot more at our website, www.statgraphics.com. If you have questions or comments, send those to info@statgraphics.com. And if you were interested at all in that Excel add-in that I showed you, we will be, as I said, sending out some pre-release evaluation copies over the next couple of weeks. Just tell us you're interested, send us an email, and we'll see that you get a copy. Now, if I can go back to my GoToMeeting dialog box, let me see whether there were any questions submitted. Well, we do seem to have only one question this time. That either means it wasn't very interesting or I explained everything very well. I'm not sure. The one question that I see so far, and incidentally, if you have more questions, go ahead down to that the section on your GoToWebinar box and submit the questions. They'll be passed on to me right now. And as usual, I'm willing to stay as long as necessary to answer all the questions. The one question I see at the moment, where did you select Monte Carlo simulation, and does it exist in version 15? It does not exist in version 15. In fact, it was not introduced until 16.1. So if you have 16.0, you should go and get your free download for 16.1. And 16.1 is under the Tools menu. It's Monte Carlo simulation, general simulation models. Okay, if you're using version 15, unfortunately, you're not going to be able to get it. Now, we did also add it to our forthcoming Excel product, also under the Tools menu. There is a section for Monte Carlo simulation, and I could have done there exactly what I did here in Centurion. Okay, anyone else with a question? If you do, go to the, there we go. Just go ahead and submit it. Here's a second question. Why would EWMA be a better chart to watch? Okay, well, the EWMA is an interesting chart in the sense that rather than putting on the chart, the control chart, only the most recent observation, it plots an average of the most recent observation and observations back into the past. Now, a standard control chart, an individual's chart, where you put the line at the mean and control limits in plus and minus 3 sigma, is great at capturing the sudden shift in the process, or the one unusual batch, for example, that's way off from where it's supposed to be. But a standard individual's chart, because the limits are so far apart, at plus or minus 3 sigma, now, as opposed, for example, to an X bar chart, where the limits are at the mean plus or minus 3 sigma over square root of n. Because you're taking individual samples, though, because control limits are far apart, a standard individuals chart is not very good at picking up a small but persistent shift away from target. It's good at picking up the sudden shifts, but not the small but persistent shifts. The EWMA, though, by averaging back into the past, is able to tighten in its control limits, much like an X-bar and R chart does. Just an X-bar chart in particular. Tighten in the limits and become more sensitive to small but persistent shifts in the mean. Now, the neat thing about what I showed you, though, is the chart that I did had both, because sometimes we're interested in picking up the sudden shift, right? The batch that all of a sudden is way off target. Whereas the EWMA is good at picking up the small but persistent shifts. And by putting both on top of each other, you get one chart that can show you both. Any single point in the red zone is a sudden shift away from target. Any movement of the EWMA outside the inner zone here indicates a small but persistent drift away from target. I'm not recommending that you replace the X chart with the EWMA chart. I'm recommending you do both so you can pick up both types of problems. Okay. A third question, is a Johnson transformation implemented besides Box and Cox? The answer is no. In the capability analysis procedure, what I showed you is you had an option of using either a normal distribution, some other distribution, or a power transformation. Now, we do have, though, in Centurion, a non-normal transformation, but it's based on Pearson curves rather than Johnson curves. For example, if I took that same data set, resistivity, okay, and went to the, that was under Analyze Variable Data Capability Analysis Individuals. Oh, actually, you can't do it as a snapstat. If you wanted to do a Pearson transformation, you'd actually have to go to the main procedure for capability, which is under Analyze. There you could put in resistivity, put in upper limit of 500, okay, do your standard analysis. But one of the options here in the full procedure is to go to the Tables button and ask for non-normal capability indices. And what that does is that actually selects from a set of curves, much like the Johnson curves, but in this case the Pearson curves, a curve with the same skewness and kurtosis as your data. And based upon that comes up with an estimate of PPK. And that's interesting. That PPK based upon the Pearson curves is about 0.84. And what was it when I did Box Cox? It was back here someplace. It was a long-term capability about 0.82 for PPK. So 0.82 with Box Cox. But if I did the Pearson curves, 0.84. So there's something similar to the Johnson transformations, not in the snapstat, but in the full-blown capability procedure, but they're called Pearson curves rather than Johnson curves. Okay. Fourth, when is the trial version of Statgraphics Sigma Express going to be available? We hope within a couple weeks. Our target is to release that product sometime in the summer. We showed it at the ASQ out in Pittsburgh last week. I wanted to show it today. It's still undergoing final testing. Most of it's already tested. It shares the same code as Centurion, but there's some of those new procedures, the statlets and some of the data handling that still needs to be fully tested. I hope within 2 weeks, though, I can send anybody who writes to us something interesting. Question 5, pertaining to EWMA versus X bar charts. Don't we want to know something if our process is shifting before the EWMA would say we're drifting? Again, I do believe that it's a good idea whenever possible, if you're doing these control charts, to do both the standard charts, and let me find a good diagram here, both the standard charts plus some sort of a smooth chart. Now, if you're lucky enough to have group data, like in an X bar and R chart, where you take 10 samples out of every batch, then it's not so important to smooth the data because you've got enough information coming from each batch that your control limits are relatively tight. Because in an X bar chart, the control limits are plus or minus 3 sigma over square root of n, where n's the group size, so it would be square root of 10, and it'd be pretty tight. The problem, and where the EWMA chart is really good, is when you can't take more than one observation at any given time. Maybe you have a continuous process. You're making a chemical of some sort, and you're measuring the impurity in a stream. Well, it doesn't make sense to measure it 5 times at the same instant, right? It makes more sense to measure it once every 10 minutes. So there's no way to naturally group the data. The exponentially weighted moving average, by smoothing back into the past, is doing much like an X bar chart would do, in that it's averaging more than just one observation in terms of being able to tighten in the control limits. So it's particularly important when you're working with data that comes one at a time, where the only good way to tighten those control limits is to do some sort of averaging. Question 6. If I am looking at actual versus set point data, and my plot of actual minus set point deviation is not normal, should I perform a Box-Cox transformation and make it normal first, and then do my ANOVA if I'm doing an ANOVA? Okay. A couple comments here. A standard analysis of variance is somewhat sensitive to whether or not data follow a normal distribution. If it's highly skewed one way or another, then yes, it would be a good idea to transform the data. Now, you can't do a Box-Cox transformation, though, if you have any data that's either 0 or negative. So you're not going to be able to, for example, take the actual data, subtract the set point, and transform the difference, because you're going to have positives and negatives. You could transform the actual and transform the set point and subtract the transformed values. That would work. And yeah, if it was significantly skewed, that might be a good idea to do that before you do the analysis of variance. The other choice is, depending upon what type of analysis of variance you're doing, if it's a fairly simple ANOVA, there are some non-parametric procedures that don't require the data to follow a normal distribution. If you have either a one-factor ANOVA or a two-way ANOVA, then it's possible to do some non-parametric procedures instead. But yes, the analysis of variance is sensitive to the assumption of normality. It's somewhat robust to it, but it is sensitive to it, and particularly if you've got long tails to the right-hand side. You know, it's going to pull one of those means way out and make one treatment look significantly better than it really is. Number 7. May these procedures be applied in exploring volatility in finance? Well, I must admit to not knowing that much about finance, but I know there are lots of applications of statistics in finance. And there's lots of people that apply these types of techniques to try to pick good stocks to invest in. And certainly volatility is something you look for when you decide what stocks to pick. Beyond that sort of general advice, I'm not the one to really give you advice on exactly how to handle financial data, although I'm sure there are lots of good applications. Question 8. Why is Shapiro-Wilkes test more powerful than KL test for normality? I think you've stumped me there on KL. Maybe this means KS, Kolmogorov-Smirnov test. If it means Kolmogorov-Smirnov test, then I can answer it. Kolmogorov-Smirnov test is a general purpose test that's meant to be able to test whether any particular distribution fits a particular set of data. Whereas the Shapiro-Wilkes test is geared just to test whether or not data comes from a normal distribution. And in general, the tighter you can make the restrictions on your test, the more powerful it's going to be. You can imagine with Kolmogorov and Smirnov, they have to handle all possible distributions, so they couldn't fine-tune the test just for a normal distribution like Shapiro and Wilkes did. That's why you'll find, incidentally, that a lot of data will pass the Kolmogorov-Smirnov test, but fail the Shapiro-Wilkes test. It's because it's a more specialized, fine-tuned test for normality. In general, the Shapiro-Wilkes test is the one I do recommend that when you're testing for normality. If you're testing whether your data comes from an exponential distribution or some other distribution, though, you need to look for a more general test like Kolmogorov-Smirnov. Number 9, Statgraphics is a powerful statistical package. According to you, how does it compare to SPSS and Stata? You know, every statistical package has its particular strengths, has particular procedures and particular people that it really gears itself toward. Okay? Statgraphics has traditionally geared itself toward people in the engineering and physical sciences. A lot of that has to do, well, one is my background. I come out of an engineering school. The second is that when we introduced Statgraphics was just around the time when Detroit in particular was getting interested in statistical process control. So all of a sudden there was a huge demand for tools to do quality control, quality assurance, design of experiments, and so forth. So our emphasis has always been toward that clientele. Also because most users in Statgraphics are engineers or practitioners rather than professional statisticians, we've tried to gear the program toward the practitioner by making it as easy as we could, by adding things like the Stat Advisor that explain the statistical results. Now, the other programs you mentioned, SPSS. Well, SPSS stands for Statistical Package for the Social Sciences. And they have traditionally added a lot of tools that social scientists need. You know, tools to analyze survey data, a lot of procedures. I mean, we have obviously some, but they have all sorts of procedures for looking at contingency tables and cross tabulations and those sorts of things. Stata, I know a little less well. One thing I do know about Stata, though, is that is that you can develop and add your own procedures to Stata. That's not something that you really can do with Statgraphics. Statgraphics gives you predefined procedures, and to some extent you can link procedures again. But if you have some brand new statistical technique you developed, there's no real programming language to help you. That said, though, we really have tried to gear Statgraphics toward practitioners. And a lot of Statgraphics users, I got to tell you, use it once a month, twice a month. So it really needs to be something that you can pick up and get back into quickly, which means relatively little syntax to learn, hopefully relatively little to remember. Okay, well, that is all the questions I see submitted till now. If you have more questions, please send them to info@statgraphics.com. Anything that can't be answered by someone else will be forwarded to me. You're also welcome to send questions directly to me, Neil@statgraphics.com.